The VCR is a complex piece of electronic and mechanical equipment that has several moving parts that are subject to wear and breakage under normal conditions. There are millions of videocassette recorders with heads which are going to require cleaning, belts which will need to be replaced due to stretching, slipping, and breakage, bearings and bushings which will wear out, gears that become stripped, motors which will burn out, and components which malfunction. Because VCRs are so complex, this tape cannot begin to cover each of the items comprehensively, but the information in this videotape should help you feel a little more comfortable with the VCR and give you solid troubleshooting background. This program is not designed to show you how to repair one particular model VCR, but rather is designed to give you a thorough understanding of how any VCR works. All VH videocassette recorders must store, retrieve, and process the video information in the same approximate manner. So by learning how one VCR works, you can better understand how all VCRs work. This program is not intended to be used as a substitute for the service manual, but is designed to be used as an aid in understanding the videocassette recorder. The VHS system magnetically places the audio and video information onto a half-inch tape. Along with the audio and video information, it also places control pulses along the lower edge of the tape. These control impulses are used to control the servo systems within the VCR. As you can see, the audio information is placed along the top edge of the tape, and the video information is placed in the middle of the tape, with the control impulses being placed at the bottom. The video information is placed onto the tape in diagonal lines. This is referred to as helical scanning. Helical scanning is used to increase the writing speed of the VCR. By increasing the writing speed, it increases the frequency range that can be recorded onto the half-inch tape. As the video heads scan the tape, each one will pick up the signal half the time. While one head is reading the video information, the other is out of contact with the tape. Each head will produce an output for approximately 1/60th of a second. This is the time necessary to produce one field of video information. To reduce crosstalk between the video heads, the VCR uses azimuth recording. Azimuth recording makes it possible to do away with the guard bands between the tracks, because the heads are rotated 6 degrees in opposite directions. This will not allow the heads to pick up a signal from the different angled patterns. If you look at the video information on this particular screen, you will see the angle on each of the video headlines. This is azimuth recording. Before we discuss the circuits which process the various signals in the videocassette recorder, we will first look at the location of the many parts used in the VCR to play and record the VHS tape. This is the tape path of the videocassette recorder. Each VCR must contain certain components to make it compatible with other VCRs. The tape starts its journey through the VCR tape path at the supply reel. When the cassette is loaded into the VCR, it will sit down on top of the supply reel and the take-up reel. As the tape leaves the supply reel, in the play or record mode, it will first go past the tension arm. The tension arm is responsible for maintaining tape back tension. The tension arm works in conjunction with a phototransistor and an LED. The phototransistor and LED monitor the amount of tape back tension and control the supply motor speed to maintain the correct back tension pressure. Next, the tape will go past the erase head. In the record mode, the erase head will have a 65 kHz AC signal applied to it, which causes the head to erase any information which might be on the tape. The erase head is only activated during the record mode, even though the tape goes across the head during the play mode. After the erase head, the tape travels past the supply roller. This roller is used to maintain tape stability before it starts the omega wrap around the video drum. After the tape passes the supply roller, it wraps around the guidepost roller post assembly. If you will notice, the tape guidepost is set at an angle corresponding to the angle of the video drum. This is to assure that the tapes wrap flat against the video head drum. From the guidepost roller post assembly, the tape does an omega wrap around the video drum. This is called an omega wrap because the tape wraps a little over halfway around the video drum. After the tape has wrapped around the video head drum, it next goes around a second set of guidepost roller post assemblies. The guide on this second assembly is also set at an angle corresponding to the angle of the video drum. This assures that the tape stays flat as it crosses the video head drum. The video head drum is placed at an angle to produce the helical scanning process required to place the video information onto the VCR tape. From the guidepost roller post assembly, the tape travels past the audio control head stack. The audio head places the audio information across the top of the tape, and the control head places its control pulses across the bottom of the tape. In the playback mode, the audio head reads the audio information from the top of the tape, and the control head reads the control pulses from the bottom of the tape. The tape next goes between the capstan motor and the pressure pinch roller. When the VCR is placed in the record or playback mode, the pinch roller will move over against the capstan motor. The capstan motor is used to control the tape speed in the VCR. From the capstan motor, the tape goes back into the cassette and winds around the spool on the take-up reel. The take-up reel is set to operate at a speed somewhat higher than the capstan motor speed, so as to keep the tape from becoming slack while it is wrapped around the video drum. The last component we shall look at is the sensor lamp. The sensor lamp is used to stop the VCR when it has reached either end of the tape. The sensor lamp works in conjunction with two phototransistors. One is located on the supply reel side, and the other is located on the take-up reel side. Placed at each end of the VHS VCR tape is a short piece of transparent leader tape. When the clear portion of the tape travels between the sensor lamp and either of the phototransistors, it will cause the VCR to go into the stop mode. If the phototransistor on the supply reel side is activated, it will cause the VCR to stop, then rewind. The tape will rewind until it reaches the transparent portion of the tape on the other end, or until the counter on the VCR reaches 0. You are provided with either a counter mode or clock mode on a VCR. If the sensor lamp burns out, the VCR will not function. It will stay in the stop mode. Most modern VCRs use infrared LEDs for the sensor lamp. The video heads determine the frequency response of the system. The amplitude of the current induced into the heads during playback depends on the frequency of the signal recorded on the tape. The higher the frequency, the higher the signal induced into the heads will be. The typical video head is a tiny electromagnet made up of two pieces of ferrite material and ultra-fine magnetic wire. The video heads will last between 1,000 and 3,000 hours, depending on the grade of tape used and the environment of the VCR. The heads protrude from the drum by 2/1000ths of an inch when they are new. When the heads wear down to 1/2 of 1/1000th of an inch, they should be replaced. The video heads are always used in pairs. Even if the VCR has more than two heads, they are still used two at a time during normal playback. The three-head VCR will have an extra head just for special effects. But during the normal playback or record modes, it still only uses two heads. A four-head VCR will have two pairs of heads. One pair will be used for standard play, and the other pair is used for long play and super long play. Each pair of heads will have different head gaps. There are two basic four-head designs: 90-degree spacing and pair spacing. In the 90-degree spacing, the heads are placed every 90 degrees on the video drum. Two of the heads are used for standard play, and the other two heads are used for long play and super long play modes. The only time the four heads are used together is during special effect modes. Pair spacing is very similar to 90-degree spacing in that two of the heads are used for standard play, and the other two heads are used for long play and super long play. Also in pair spacing, the only time the four heads are used together is during the special effects mode. Pair spacing's advantage is its vast improvement in special effects. The video heads are always placed at the bottom of the video drum in the VHS system. The heads in the video drum can have head gaps as small as 12 millionths of an inch. This is as small as the head gap can be made without causing a magnetic short in the video heads. If the head gaps become plugged, it will cause the VCR to lose the picture completely. If only one head becomes plugged, it will cause the picture to produce large amounts of dropout. Dropout will look like snow or white specks going across the screen. Once the heads become plugged, they must be cleaned to restore the video image. We will see how to do this later in the program. Each video head records one complete field as it travels diagonally across the tape. The vertical field rate in a color television is 59.94 Hertz. So the tape head must read 59.94 fields per second to lock in sync with the vertical field rate of the color TV. Since the two heads are used on the video head drum for playback and record, each head therefore must record 29.97 fields per second. The video head drum must rotate at exactly 29.97 revolutions per second. To control the video head drum at this exact speed, a closed-loop servo system is used. The closed-loop servo system must have a reference voltage which sets the speed of the system and a feedback voltage which tells the system how fast it is moving. The servo system will compare these two signals and produce an output voltage which will cause the servo motor to operate at the correct speed. This correction voltage will either increase or decrease the speed of the motor. In addition to controlling the speed of the video drum, the phase of the video drum must also be controlled. This is necessary to ensure that head A scans the track recorded by head A, and head B scans the track recorded by head B. The feedback signal for the speed loop is referred to as the FG pulse. The FG pulses are developed by a generator in the video head drum assembly. The generator consists of an 8-pole magnet installed in the drum rotor and a detection coil mounted in the stator. The feedback signal for the phase loop is called the PG pulse. The PG pulse is also referred to as the 30 Hz drum tack pulse. The PG pulse is used in both the record and playback modes. The PG pulse is developed by a pulse generator installed in the lower part of the video drum shaft. The PG pulse is used to determine the video head switching phase, which in turn provides correct tracking for the video drum heads. During record, the broadcasted vertical sync pulse is used as the reference signal. The phase loop pulse width modulation circuits divide the vertical sync pulse in half to produce the 29.97 Hz reference signal. During playback, the 3.58 MHz signal is divided down to the 29.97 Hz reference signal required for the circuit. The reference signal and the PG signal are compared in the pulse width modulation circuit to determine the correction necessary for proper phasing of the video drum. The outputs of the phase loop and the speed loop are added together in the summing circuit to determine the drive voltage which is sent to the video drum drive motor circuitry. The speed loop is essentially the coarse speed control for the video drum servo system. The speed loop will cause the video drum to operate at a speed somewhat higher than the 29.97 revolutions per second. The phase loop pulse width modulation circuit will have 5 inputs and 2 outputs. This circuit is usually contained in a single integrated circuit. When the slow or search modes of the VCR are used, it places the pulse width modulation circuit at 50% duty cycle. When this circuit is placed in the 50% duty cycle, it will output 4 volts into the low-pass filter network. The low-pass filter then delivers 2.6 volts into the summing circuit. The phase loop circuit also has a 30 Hz control signal which is sent to the head switching circuits. This signal is used to control the head switching times during record and playback. This chart shows a servo system used to control the speed of the video drum during record. This circuit uses the vertical sync pulses as the reference signal. Since the vertical sync pulse is a 59.94 Hz signal, it must go from the sync separator into a divide by 2 circuit. The outputs of the divide by 2 feeds into 2 separate circuits. One is a square wave generator, which is used to produce square wave pulses, which are fed into the control head to be recorded onto the bottom of the VHS tape. As we shall see, these pulses are used in playback to help control the speed of the capstan motor. The other signal path coming from the output of the divide by 2 circuit goes to the sample and hold circuit. This signal controls when the sample and hold circuit samples the signal from the ramp generator. The pickup coil detects a rotating magnet placed on the video drum. As the magnet passes the pickup coil, it will produce a voltage into the coil. The voltage from the pickup coil is then fed into a delay circuit. This circuit will delay the signal for a predetermined amount of time. The output of the delay circuit is fed into a ramp generator. When the positive signal from the delay circuit reaches the ramp generator, it will start producing a ramped voltage. This ramped voltage is then fed into the sample and hold circuit. When the signal from the divide by 2 circuit turns on the sample and hold circuit, it will sample the voltage produced by the ramp generator. The output voltage from the sample and hold circuit controls the current output from the DC amplifier. The DC amplifier directs the current into the brake coil, which is on the video drum shaft. If the video drum is turning too slow, then the pickup coil pulse will reach the ramp generator too late. This will cause the sample voltage to be too low, and the low voltage being applied to the DC amplifier will cause it to produce less current at the output. With less current being applied to the brake coil, it will cause the video drum to increase in speed. In the playback mode, the control head will read the square wave pulses which were placed at the bottom of the VHS tape during the record mode. These pulses are then fed into the pulse amplifier and are used to turn on the sample and hold circuit. A small magnet is placed on the video drum next to one of the heads. This magnet rotates with the drum and passes over the pickup coil, which is mounted on the stationary part of the video assembly. Each time the magnet passes over the coil, a pulse is induced into the pickup coil. The pulse from the pickup coil goes through a delay circuit and into a ramp generator. When the pulse reaches the ramp generator, it begins generating a ramp voltage into the sample and hold circuit. The sample and hold circuit will sample the ramp voltage when it is told to do so by the pulse amplifier. The output from the sample and hold circuit is determined by how high the ramp voltage has risen at the time the ramp voltage is sampled. The sample and hold circuit also contains a sample and hold capacitor, which charges to the value of the ramp voltage when it is sampled. The amplitude of the voltage on the hold capacitor will determine the output of the DC amplifier. The output current from the DC amplifier is fed into the brake coil, which is mounted on the video drum shaft. The more current applied to the brake coil, the slower the video drum will rotate. If the video drum is rotating too fast, the pulses from the pickup coil will arrive too soon, and when the pulse amplifier activates the sample and hold circuit, the ramp voltage will be too high. This will cause the charge on the hold capacitor to increase. When the charge on the hold capacitor increases, it will cause the DC amplifier to increase its output current into the brake coil. When the current is increased in the brake coil, it will cause the video drum to decrease in speed. The capstan motor is used to control the tape speed through the VCR. There are two major parts in the capstan servo circuit: the phase loop portion and the speed loop portions. The capstan servo is similar to, but not identical to, the video drum servo. The capstan phase loop uses a 3.58 megahertz signal as the reference signal. If you recall, a servo system needs a reference signal and a feedback signal to be a closed loop system. During playback, the feedback signal is taken from the pulses recorded at the bottom of the tape on the control track. During record, the feedback signal is derived from the capstan FG signal. The capstan FG signal has three different frequencies, which are dependent to the tape speed. In the standard play mode, the FG signal is a 2160 Hz signal. In the long play mode, the FG signal is 1080 Hz. And in the super long play mode, the FM frequency is 720 Hz. The FG signal is fed into the slow speed circuit of the capstan servo system. In the playback mode, the control head will read the pulses which were placed on the tape during the record mode. This signal is then amplified and fed into the phase loop part of the servo system. The control pulses are then compared to the divided down 3.58 megahertz reference signal. The phase loop will have two outputs. One is a 437 Hz signal, which is fed into a low-pass filter, then into the phase control circuit. The other output goes to the speed loop portion of the servo. There are 6 inputs going into the phase loop. One is the amplified control head pulses. The second one is the 3.58 megahertz reference signal. The third one is the speed loop. The fourth one is from the search mode circuit. The fifth one is from the record circuit. And the sixth one is the cylinder lock signal. During the special effects, such as slow motion, pause, or cylinder lock condition, the pulse width modulation part of the phase loop will generate a fixed 50% duty cycle. In effect, the capstan phase control is removed from the circuit. The capstan speed loop circuit will develop a correction voltage by taking the difference in frequency between the capstan FG pulses and the divided down 3.58 megahertz signal, which is derived from the phase loop circuit. The capstan speed adjust controls the level of the DC correction voltage for the speed loop. The correction voltage is combined with the phase control signal and is then applied to the capstan drive circuit. The drive circuit is used to operate the capstan motor. There is also a signal leaving the slow speed circuit and is fed into the video drum drive circuit. This is a correction voltage which is added to the video drum drive signal. The method that the video cassette recorder uses to record the color signal is quite complex. In the VCR, the chroma signal is changed considerably. First, the 3.58 MHz color burst is removed from the composite video signal. Then it is heterodyned to a lower frequency. It is down converted to 629 kHz in the VHS system. This is achieved by mixing the 3.58 MHz color burst with a phase-shifted 4.208 MHz signal. The difference between these two signals is then recorded on the tape. The chroma signal is limited to a 1 MHz bandwidth. The composite video signal is fed from the tuner into a bandpass filter. The bandpass filter rejects all frequencies except the 3.58 MHz color signal. From here, the signal travels into an amplifier which boosts the strength of the signal. The color signal next travels through the expander circuit, which boosts the color burst by 6 dB. The burst is then fed into an emitter-follower circuit, which has an amplification factor of less than 1. The emitter-follower is used as an impedance matching device. The signal then travels into the automatic color control circuit. The automatic color control is used to control the amplitude of the color information. The control voltage in the ACC circuit is derived from a burst gate pulse circuit, which is controlled by the horizontal sync separator circuit. The signal from the ACC circuit is fed into the main converter. The output of the main converter is tuned to 629 kHz. The main converter heterodynes 3.58 MHz color signals with a 4.208 MHz signal to produce the 629 kHz color signal. The 3.58 MHz oscillator and the 629 kHz signal from the automatic frequency control circuit are mixed together in a separate converter stage to produce the 4.208 MHz signal required for the main converter. The 629 kHz signal from the AFC circuit is shifted or rotated 90 degrees on every one horizontal line period. 208 MHz signal is passed through a band pass filter, which rejects all frequencies except the phase-shifted 4.208 MHz signal. The 629 kHz color signal travels from the main converter into a low-pass filter. The low-pass filter allows only the phase-shifted 629 kHz signal through and blocks the higher frequencies. From the low-pass filter, the signal travels through another emitter-follower circuit. Here again it is used as an impedance matching device. The signal goes from the emitter-follower through the color level control. The color level control is used to set the color level being fed into the record amplifier. When the 629 kHz phase-shifted color signal is fed into the record amplifier, it is mixed with the luminance signal. The luminance signal attenuates the lower 1 MHz portion of the band to allow room for the color signal. From the record amplifier, the combined signal is fed into the head switching circuit for the video heads. The head switching circuit passes the signal to the rotary transformers in parallel. The rotary transformers then pass the combined YC signal to the video heads. The video heads magnetically transfer the video information onto the VCR tape. In the playback mode, the color signal is removed from the luminance signal, then the 629 kHz color signal is raised back to a replica of the original 3.58 MHz signal. The video information is read by the heads, then passed into separate preamp stages. From the preamp, the signal is fed into an equalizer amplifier circuit. The equalizer amp is used to get the video level for each head. The signal travels from the equalizing amplifier and goes into the head switching circuit. The head switching circuit causes the heads to play back in series. The heads are switched 6 horizontal lines before the start of the vertical blanking pulse. From the head switching circuit, the signal is fed into the balance adjust. The balance adjust is usually a potentiometer and is used to set the signal level from each head so they are the same amplitude. From the balance adjustment, the signal travels through a mixer circuit. The mixer circuit combines the signals from both heads. From here, the signal is passed into the FM level adjust potentiometer. This is used to set the resting frequency of the FM signal to 3.4 megahertz for the VHS system. After the FM level adjust, the luminance signal is trapped out by means of a high-pass filter. The 629 kilohertz color signal is sent to an amplifier, where the color signal is boosted. The amplifier also traps out any of the audio bias signal which might be present in the video signal. Next, the color signal is passed through a low-pass filter, which allows only the 629 kilohertz color signal through. After the low-pass filter, the color signal is further amplified, then sent into an emitter-follower circuit. The emitter-follower circuit is used as an impedance matching device. From the emitter-follower, the signal travels through the automatic color control circuit. The ACC circuit is controlled by a burst gate circuit and a burst detector circuit. The automatic color control circuit is used to keep the overall level of the color signal constant. The 629 kilohertz color signal is next fed into the converter circuit along with the 4.208 megahertz signal. The output of the converter circuit is tuned to the 3.58 megahertz. The 4.208 megahertz signal is a phase-locked rotary signal like the one used in the record mode. The 3.58 megahertz color signal at the output is a replica of the original color signal with no rotation and no instability. From the converter, the signal next goes through a bandpass filter, which is used to allow only the color signal through and block all other frequencies. The signal travels from the bandpass filter into another amplifier stage, where the chroma signal is boosted in amplitude. This amplifier stage is also fed by a compressor circuit, which operates whenever there is a burst gate pulse to reduce the gain of the amplifier. The compressor circuit is necessary to restore the burst signal to a normal level at playback. If you remember, in the record mode, the expander circuit boosted the color signal by 6 dB. The compressor circuit is designed to cause the amplifier to attenuate the signal by 6 dB when there is a burst gate pulse. The color signal is next fed into a 1H delay line circuit. This circuit is used to remove crosstalk between the two video head channels. This crosstalk occurs in the LP mode to some extent, and to an even greater extent in the SLP mode. From the one horizontal delay line circuit, the signal is fed into another amplifier, where the signal is once again boosted in amplitude. From the amplifier, the signal is fed into the killer amplifier. The killer amplifier is a switch circuit that allows the color signal to pass only when there is a color signal present in the composite video signal. The killer amp is controlled by a signal from the killer circuit. Next, the color signal is fed into the color adjust potentiometer. This pot is used to set the color level, being fed into the luminance record mixer circuit. The YC mixer combines the luminance and chroma signals back into the composite video signal. From here, the signal is fed through the clamp mute circuit. The clamp mute circuit is used to hold the voltage at specified levels for the RF modulator. The signal next travels into the EEVV switch. The term EE stands for electric to electric and is used to ensure that the EE output switches to the black and white mode when signal conditions are bad. When the heads and tape are involved in normal record and playback modes, the term VV or video to video is sometimes used. From the EEVV switch, the signal is fed into the channel 3, channel 4 RF modulator, so the VCR output signal can be viewed on a conventional TV set. The luminance circuits in the VCR are used to record the black and white portion of the composite video signal. The luminance signal is converted into an FM signal that deviates from 3.4 to 4.4 megahertz in the VHS system. Additional sidebands beyond these frequencies are created in the modulation process. The lower sidebands below 1 megahertz are attenuated to allow room for the lower frequency chroma signal. The video input travels from the tuner to the low-pass filter. The low-pass filter passes the video frequencies, but rejects the 3.58 megahertz color signal. From the low-pass filter, the luminance signal is fed to the AGC circuit, which is used to keep the output level constant, regardless of the input level of the video signal. Next, the video signal is amplified and passed into another low-pass filter, which serves as a 3.58 megahertz trap to remove the color signal. This trap is usually a comb filter that eliminates the chroma portion of the video signal. The video amplifier also feeds into a sync separator circuit. The pulses from the sync separator circuit are fed into the automatic gain control detector circuit. The automatic gain control detector circuit then feeds into the AGC adjustment. This is usually a potentiometer used to control the amount of gain control going into the automatic gain control circuit. The pure video signal is then applied to the video amplifier, which is used to boost the amplitude of the video signal. From the video amplifier, the video signal is fed into a switch circuit and a nonlinear emphasis circuit. The nonlinear emphasis circuit emphasizes the luminance signal by different amounts, depending on the tape speed. More high-frequency boost is added in the LP and SLP modes than in the SP modes. This is because there is more high-frequency response loss in the long play and super long play modes. The switch circuit that the video amplifier feeds into is used to bypass the nonlinear emphasis circuit when in the standard play mode. The video signal travels from the nonlinear emphasis or switch circuit, depending on the tape speed, into the FM deviation adjust. This is usually a potentiometer that is used to set the FM modulation level. From here, the signal is fed into another video amplifier. The boosted video signal from the video amplifier is then fed into the clamp circuit. The clamp circuit is used to ensure the DC voltage level of the video sync tip remains constant, regardless of the input from the video amplifier. This keeps the sync tip at 3.4 megahertz. The clamped signal is then fed to the pre-emphasis network, where the high-frequency video signals are emphasized to improve the signal-to-noise ratio. This circuit is necessary to reduce noise in the video signal. The pre-emphasis and amplifier stage provide the standard high-frequency boost that is required for any type of magnetic recording. The video signal is next fed into a clipper circuit, which is used to clip off the top and bottom overshoots in the video signal that are caused by large amounts of pre-emphasis. The clipper circuit is used so the deviation limits are not exceeded. Next, the video signal is fed into the FM modulation circuit. The FM modulator also receives the 30 Hz FF pulses from the video drum. The FM modulator used in most VCRs are nothing more than simple free-running multivibrators that are designed to run at a specific frequency when the horizontal sync pulses are present. The information in the luminance signal will cause the frequency of the multivibrator to increase. The signal from the FM modulator is next fed through an emitter-follower circuit, which is used as an impedance matching device, into a high-pass filter. The high-pass filter allows the video signal through and blocks the lower end of the FM signal so as not to interfere with the 629 kilohertz chroma signal, which is added later in the signal path. The record level adjust potentiometer is used to set the FM modulation level. Next, the signal is fed to the squelch circuit, which is used to prevent the signal from being fed to the record amplifier for about 1.5 seconds after the cassette has been loaded. This prevents the recorded signal from being erased if the tape runs near the drum in the middle of the loading process. From the squelch circuit, the FM modulated video signal is fed into the record amplifier, where it is mixed with the 629 kHz chroma signal and amplified. From here, the signal is fed into the head switching circuit and then into the rotary transformer, where they are combined. The luminance chroma signal is then sent to the heads in parallel. The heads then magnetically transfer the video information onto the VHS tape. In the luminance playback mode, the video information is picked up from the tape by the heads, then passed through the rotary transformer into the preamps. The preamps boost the signal level and pass the video signal into another amplifier for more amplification. From the second amplifier, the signal is passed through the head switches. The head switches cause the heads to read one at a time. This helps eliminate the overlap between the signals coming from the heads. Next, the signal is sent into the head balance pot. This is used to set the video signal so there is an equal signal from each head. From here, the signal goes through a mixer circuit and into an FM level adjust pot. This is used to set the level of the FM signal coming from the head circuits. After the FM level adjust, the 629 kHz chroma signal is removed and sent to the color circuits. The signal also goes into a video amplifier. The video amplifier has a comb filter in it that will block the 629 kHz color signal. From the video amplifier, the signal is passed through a high-pass filter, which is also used to reject the low-frequency color signal. After the high-pass filter, we have a pure luminance signal, which is still an FM signal that deviates from 3.4 to 4.4 megahertz. The pure video signal is next sent through an emitter-follower circuit, which has a gain of less than 1 and is used as a buffer device. After the emitter-follower, the signal is sent into a dropout compensator circuit. The dropout compensator circuit prevents the picture deterioration by supplying a one horizontal line scan if the FM signal is partially missed. The video signal is then fed into a double limiter circuit, which consists of high-pass filters, first limiter, low-pass filter, mixer, and second limiter. The double limiter removes any AM from the FM signal. Next, the luminance signal is fed into the FM demodulator circuit. The FM demodulator is used to recover the original modulated wave from the carrier which it was modulated with. The output of the FM demodulator will be from 0 to 4.2 megahertz. The demodulated signal is then sent to a video amplifier to boost the signal strength. The boosted signal is then fed into a low-pass filter. The low-pass filter will allow only the luminance signal through. The luminance level is then set by the Y level adjust and fed to the de-emphasis circuit. The de-emphasis circuit is used to reduce the level of the higher video frequencies during the tape playback, so they compensate for the pre-emphasis which was applied during record. This restores an overall uniform response with an improved signal-to-noise ratio. The signal is then fed into an edge noise cancel circuit, which is used to remove any noise from the video signal, and into an emitter-follower circuit, which is used as an impedance matching device. The luminance signal is next fed into a switch circuit and a compensator circuit. The switch circuit is used to bypass the compensator circuit when the VCR is used in the standard play mode. During the long play and the super long play modes, the compensator will return the nonlinear emphasis which was supplied during record. The compensator will alter the frequency's response of the amplifier system to achieve the specified results. The signal flows from the compensator switch circuits into an emitter-follower circuit. The signal then feeds into the feedback amplifier circuit. The nonlinear de-emphasis circuit is turned on during the super long play mode. The compensator and nonlinear de-emphasis circuit returns the nonlinear emphasis which was supplied during record. During a color broadcast, the signal is fed into the low-pass filter, then into the video amplifier. But during a black and white broadcast, the low-pass filter is bypassed by action of a switch circuit at the output of the video amplifier. The low-pass filter is used to remove any noise that would arise if the video signal overlapped the demodulated chroma signal. The signal next travels from the switch into a high-pass filter. The high-pass filter will allow only the luminance signal through and will block all other frequencies. The signal next goes into a limiter circuit. The limiter circuit is used to remove any clips from the luminance signal. The signal next goes into a noise cancel circuit. The noise cancel circuit removes any noise from the video image. The signal is next sent into the mixer circuit. The mixer circuit combines the 3.58 MHz color signal with the video luminance signal. From here, the signal is fed through the clamp mute circuit. The clamp mute circuit is used to hold the voltage at a specified level for the RF modulator. Signal next travels to the EEVV switch. As you will recall, EE is electric to electric and assures the EE output switches to black and white mode when the signal conditions are bad. When the heads and tape are involved in normal record and playback, the VV or video to video is used. From the EEVV switch, the signal is fed into the channel 3, channel 4 RF modulator, so the VCR output can be viewed on a conventional television set. This part of the program is devoted to learning the audio circuits in the VCR. Most modern video cassette recorders have the ability to play back and record in stereo. In older VCRs, the audio head used a 1 mm track. This was replaced by 2 audio heads mounted on the same audio control head stack. Each of these heads uses a much narrower track when compared to the mono system. These narrower stereo heads result in a lower signal-to-noise ratio and generally require some form of compensation. Therefore, most modern VCRs compensate for the lower signal-to-noise ratio with the Dolby noise reduction system. The heads of the stereo system will typically be 350 micrometers wide. Here we see the relationship between the monaural and stereo audio tracks. As you can see, the mono head is much wider than the stereo heads. There will be a 0.3 millimeter guard band between the stereo heads. This provides a good separation between the 2 audio channels. Background noise is common in all audio tape recording systems. Background noise occurs in the frequency range of about 5 to 10 kilohertz. There are several types of Dolby systems presently available. Most VCRs use the Dolby B system, which provides noise reduction in the frequency range of 5 to 10 kilohertz. In the record mode, the audio signal is first processed by the FM detector. The FM detector is used to recover the modulated signal from the FM carrier signal. Next, the signal goes into the attenuator. The attenuator is usually a resistive network that reduces the amplitude of the incoming signal without causing appreciable phase or frequency distortion. The attenuator is necessary to avoid overloading the audio circuits by strong signals. The signal travels from the attenuator and goes to the monitor amplifier. The monitor amplifier is used to set the gain of the signal, which is fed into the Dolby encoder circuit. As was stated earlier, the Dolby circuit is a noise reduction system whereby the recording signal is compressed and the playback signal is expanded. This results in a reduction of background noise. The Dolby encoder system is usually contained in a single integrated circuit. The signal is next processed by the record amplifier. The record amplifier is usually an audio amplifier which is designed to amplify signals within a frequency range of about 15 Hz to 20 kHz. From the record amp signal, it's fed into the mixer circuit. The mixer circuit combines the separate input signals linearly in the desired proportion to produce the output signal. The mixer mixes the audio signal and a signal from the bias oscillator. The bias oscillator is used in magnetic recording to generate an AC signal in the range of 65 kHz for the purpose of magnetic biasing to obtain a linear recording characteristic. The bias oscillator also serves as the erase oscillator. The combined audio and bias signals are then directed into the line amplifier. During record, the system control generates a high head switching command, which turns on the head switch and provides the audio head with a ground return path so that the combined audio and bias signals can be recorded by the audio head. The line amplifier is used to supply the audio head with a signal at a specified level for proper recording. The signal travels from the line amplifier to the audio head. The audio head is a magnetic type and is used to read and write the audio information onto the VCR tape. The audio head changes the magnetic state of the tape in record and reads this change in playback. In the playback mode, the audio head reads the audio information and directs the signal into the line amplifier. The line amplifier boosts the audio signal and feeds it into the playback amplifier. The playback amplifier further amplifies the modulated signal and directs it into the Dolby decoder circuit. The Dolby circuit provides a clean, noise-free audio signal, which is then processed by the monitor amplifier. The monitor amplifier sets the gain of the signal and feeds it into the attenuator. The audio volume control is also fed into the attenuator to set the gain of the audio signal. Next, the signal travels to the RF modulator. The RF modulator produces a channel 3 or channel 4 signal, which is then fed into the TV receiver. The audio circuits for most VCRs are straightforward direct paths from input to output. Troubleshooting the audio system involves basic signal tracing with devices such as meters and oscilloscopes. If you are troubleshooting a stereo system, compare the readings between the channels. The audio level readings should be essentially the same for both channels. The service manual will usually give some hint as to what the audio signal level at the outputs of the various stages should be. This 9-step troubleshooting procedure may be used for any of your repair jobs, but it has been altered to be used for troubleshooting VCR. The job is to get as much information about the problem as possible. You should ask the customer questions. For example, how is the VCR acting at the present time? Did the trouble start gradually or suddenly? Did you notice any other problems? As the customer answers the question, make notes so you can refer to them at a later point in time. The second step is to confirm the problem. You should operate the VCR and check its performance in all the modes of operations. This will show you what the VCR is and is not doing. Try playing a known good tape. If it does not play back, make sure all the controls are set correctly and the tracking is set correctly. Even if the video is not working, you may still have audio. If the audio is working, then the servo circuits must be working properly. Try taping a blank tape, then playing it back. If it does not play back, then put the recorded tape in a good VCR and see if it did record. You should try recording on the VCR with at least 2 different speeds. In step 3, you will reason out the problem. After you have tried the VCR and found out what it is and is not doing, use your understanding of the VCR circuit to determine where it might be in the VCR. For example, when the VCR was hooked up in the record mode, you got a picture on TV, and the tuner, video, IF amplifier, demodulator, video amplifier, and modulator must all be working. If you did not get a picture, start with these circuits. The failure of the VCR to work in the record or playback mode would indicate problems in the heads or head circuits. This would be in the heads, rotary transformer, switches, record amplifier, equalizer circuit, or in the power supply. A problem of no color would be in the chroma circuits. Step 4 is looking for surface defects. When the VCR is operating, look for mechanical problems. Everything should be working smoothly. Listen for unusual noises. Inspect the heads for dirt and wear. Inspect the belts and gears. A broken gear can cause timing problems, or a stretched belt can cause a number of problems in the VCR. Inspect the printed circuit board for burnt components, or broken wires, or bad solder joints. In step 5, you should determine the defective circuit. You will need the service manual for the next 3 steps. By using the oscilloscope and voltmeter, You should check for proper voltages and signals in the suspected section. The service manual will give you the values you should obtain and tell you how the VCR should be set up. In step 6, you determine the defective circuit. To isolate the defect down to one circuit usually requires voltage and resistance measurements. Many of the circuits in the VCR will be contained in a single IC. Before assuming one of the ICs are defective, make sure all the external components are good and the proper signals are reaching the IC. If the integrated circuit is defective, determine what caused the IC to fail. In step 7, you will determine the defective part. Many times after completing step 6, you will have already narrowed the problem down to a defective part. At times there may be more than one defective part. If you find a shorted component in the circuit, you should check the values of the components used by that part of the circuit to make sure none have changed values. Step 8 is simply to replace the defective part. In step 9, you should once again check the operation of the VCR to be sure it's operating as it should be. There are times when the VCR will have more than one problem, and this step will show you if there is a second problem. The VCR should be checked before and after it has been reassembled. The first step in troubleshooting luminance circuits is to play back a test tape or a known good tape. If the playback from the tape has poor resolution, then look for an improperly adjusted noise canceller circuit or for a bad response in the video head preamps. Adjustments: study the stair-step or color bar signals for any transients at the leading edges of the white bars. If the playback has excessive snow, first try adjusting the tracking control. Solve the problem, then clean the video heads before making any adjustments. Snow can also result from mistracking due to a mechanical problem. Snow resulting from mechanical problems is usually a result of a bad alignment in the tape path. If the playback produced smudges on the leading edges of the white parts of the test pattern, the problem is probably in the preamps or in the adjustment that matches the heads to the preamps. Smudging usually occurs when there is distortion on the high end of the video signals. If you see a herringbone pattern, which will look like color bars floating through the picture, look for a carrier leak. You will probably find an unbalanced condition in the FM demodulator or limiter circuits. If there is an excessive carrier leakage passing through the demodulator, this will result in a negative picture. The first step in troubleshooting the chroma circuits is to play back a test tape or a known good tape. Next, try adjusting the controls on the VCR which pertain to color. Also, try adjusting the tracking control. Most of the color circuits in the VCR will be contained within 3 or 4 ICs. If the inputs going to the ICs are good, there is an abnormal or absent output, then you must replace the IC. Before replacing any ICs, you must first check any associated circuitry pertaining to the suspected chip. The fixed input to the color converters will come from the same source for both record and playbacks. Remember, the main converter is fed with the chroma signal and a 4.208 MHz signal. If you get good color on playback but not on record, then the problem will definitely be in the record circuits. If you get no color on the playback, then the problem could be in the playback circuits or in the source supplying the 4.208 MHz signal. Use the oscilloscope to check the main converter to see if you have the 629 kHz signal at one input and the 4.208 MHz signal at the other input. Then check for the 3.58 MHz signal at the output. If the color hue of the picture is not correct during playback, then check the color subcarrier frequency with an oscilloscope or a frequency counter. It should be 3.579545 megahertz. A barber pole effect indicates a loss of color sync. This is usually due to troubles in the automatic frequency control circuits. Make sure the AFC circuit is receiving the horizontal sync pulses and that the voltage-controlled oscillator is on frequency. Automatic color control circuit. This could also be caused by a bad head on the video drum. If there is a bad head, the flicker will also occur in the luminance signal. VCRs are susceptible to wow and flutter problems. Wow and flutter are usually caused by tape transport speed fluctuations. With wow and flutter problems, the picture will become unstable and the audio will become quivering or garbled. The longer fluctuations below about 3 Hz are called wow, and shorter fluctuations between 3 to 20 Hz are called flutter. Wow and flutter can be caused by mechanical problems or by servo problems. Amount of wow and flutter in a VCR, use the low frequency tone recorded on an alignment tape and a frequency counter or oscilloscope connected to the audio circuit at some convenient point. Usually the low frequency tone will be about 333 Hz. An acceptable amount of wow and flutter is 0.03%. A VCR has interchange problems when it can play back tape that was recorded on the same VCR, but cannot play back tape recorded on another VCR. It is almost always caused to an improperly adjusted tape path. The easiest way to adjust the tape path is to monitor the RF output from the video heads during playback and adjust the tape height to produce a maximum uniform RF output from a factory alignment tape. The output is usually monitored at a point after the head switching so that all heads are monitored. You should follow the manufacturer's adjustment procedures. There are several types of belts used in the VCR. There are special film belts made of carton, mylar, and other similar types of material. These belts seldom wear out or break in the VCR, but the rubber belts used in the VCR must be replaced about every 1,500 hours of use. Rubber belts will deteriorate with age and use. When one of the belts being used in a critical application wears out, it will cause the VCR to shut down. When this happens, the belt must be replaced. It is a good idea to replace all the belts when you must replace one of them. The older model machines used as many as 8 belts, while many of the newer machines use only 1. The VCR we are working on has only 2. As you can see, replacing the belts in this machine is a very easy job. To replace the smaller belt requires removing the old belt and installing the new belt in its place. To replace the belt on the capstan drive, you must remove the 2 screws holding on the bracket over the bottom of the capstan assembly. The old belt and install the new one. After the new belt is in place, you simply replace the bracket back to its original position. Most of the belts are accessible by removing the bottom cover of the VCR. Make sure the machine is unplugged so you do not get a shocking surprise while you are replacing the belts. When replacing the belts in any VCR, you should check with the service manual for the proper procedures. When the playback picture starts to deteriorate with large amounts of dropout, it is time to clean the heads in the VCR. The video heads become dirty due to particles of the tape becoming lodged in the video head. If enough tape particles become lodged in both the heads, the VCR will lose the picture completely. The audio will still function properly, but the picture detail and color will not be present. Usually, when it is time to clean the video heads, it is time to clean the entire tape path. After you have gained access into the tape path, you will need foam tip swabs and a cleaning solution of alcohol or a Freon-based solution. Never use the spray-on type Freon, because the temperature change induced by the spray may damage the ferrite material that the video heads are made out of. Always use a solution in a bottle. Moisten the foam tip swab with the cleaning fluid, then place the swab against the side of the video drum and gently rotate the video drum from the top with your finger. Be careful not to touch the side of the video drum with your finger. Never use a top-to-bottom motion with the foam tip swab, as this could destroy one or both of the delicate video heads. Never use cotton swabs, because if a piece of lint from the cotton swab becomes lodged in the video head, it will destroy the head. Never apply heavy pressure to the top of the video drum while you are rotating it with your finger. Clean the entire surface of the video head. After you have thoroughly cleaned the video drum, inspect the foam tip swab. If it is dirty, replace it with a new one. Once again, moisten the foam tip swab and clean the audio control head stack using a light side-to-side motion. Clean the audio control head stack, you should clean the erase head. When cleaning the erase head, use a light side-to-side motion. Next, clean the guide post roller post assemblies. Clean both the guide posts and guide rollers. After cleaning the guide post roller post assembly, clean the tension arm. Clean the supply roller. Next, clean the capstan motor shaft. After you have cleaned the capstan motor shaft, clean the pressure pinch roller. By the time you are finished, you should have cleaned everything which comes in contact with the VHS tape. A VCR is new. The video heads will protrude from the drum by 0.02 of an inch. As the heads rotate across the tape, it creates a friction on both the heads and the tape. This friction will eventually wear down the video heads, and they must be replaced. After playing 190-minute tapes in the standard play mode, the heads will have traveled approximately 2,000 miles. It is easy to see why they wear out. Generally, a head-related problem will affect the entire picture all the time. It will affect the picture in both the record and playback modes. If only one head is involved, the picture will have large amounts of dropout. If both heads are involved, the picture may be missing entirely. The video heads in the VHS machine are placed in the upper cylinder, and the entire cylinder rotates. To replace the heads, you must replace the entire upper cylinder. To replace the video drum, you must unsolder the 4 wires on top of the drum. There will be 2 pairs of wires on the 2-head system. There will be a yellow wire and a brown wire for one head, and a yellow wire with a red wire for the other head. After these wires have been unsoldered, you must next remove the 2 screws which hold the upper cylinder in place. After the screws have been removed, you gently remove the upper cylinder from the shaft. When you install the new upper cylinder, you must use extreme caution to avoid touching the heads on the video drum. The cylinder should be installed so the colored wires can be connected to the correct terminals on the relay board. The 2 holes through which the mounting screws pass should line up with the holes in the lower drum. After the cylinder has been installed and lined up properly, the 2 screws which hold the upper cylinder in place should be put back in. After you have completed this operation, clean the entire upper cylinder. Before you replace the cover back on the VCR, you should operate the VCR in both the play and record modes. If it works satisfactorily, then replace the cover and operate it again in both the play and record modes. The machine should be operated with a test tape or a known good tape in the play mode to check for compatibility. If the VCR does not play back the test tape properly, then the tape path must be aligned. To align the tape path in the VCR, it it is recommended that you follow the procedure outlined in the service manual for the machine you are working on. There are generally two places to adjust the tape path before it goes across the video drum, and two places to adjust the tape after it has crossed the video drum. How to remove and replace the idler roller assembly. The idler roller assembly will wear out and cause the VCR to stop functioning. These assemblies are mounted in an assortment of ways. You will see how to replace one type of idler assembly. This idler assembly is held in by a small lock washer mounted on the shaft protruding through the assembly. Before the idler roller can be removed, there is a spring located above the idler roller assembly. This spring is attached to a lever that is placed against the supply reel brake band. After the spring has been released, the small lock washer located on the shaft must be removed. Once the lock washer has been removed, the idler assembly must be replaced. On some models, you need only replace the idler wheel. Here we see a close-up of the assembly. To replace the idler assembly, you simply place it onto the shaft and push it down. Once it is down, pull out on the idler wheel a small amount and push it the rest of the way down. After the assembly is in place, the lock washer must be placed back on the shaft and pushed down to the top of the assembly. After the lock washer is in place, the spring must be reconnected to the lever it was removed from. As with any service job, when you are finished, try the VCR to make sure it functions properly. When the drum motor becomes defective and no longer functions, it must be replaced. First, the video head cylinder must be removed. As you have seen previously, you unsolder the wires on top of the video drum and remove the two screws which hold the drum cylinder in place. Next, carefully remove the drum cylinder, being careful not to touch the video heads. After the cylinder has been removed, you must remove the metal cover which shields one of the plugs on the video drum motor. VCR over and remove the three screws which hold the drum motor into place. The motor can be removed from the top of the VCR. After the motor is removed from the VCR chassis, the plugs on the motor must be disconnected. At this point, the drum motor should be completely isolated from the machine. Here, video drum motor. Take the new drum motor and connect the plugs in the correct sockets. Then correctly align the motor back into the VCR chassis, making sure the mounting screw holes are properly aligned. Next, replace the three screws which were removed from the motor assembly. After the motor is firmly secured, replace the metal shield that goes over the plug. Finally, reinstall the drum cylinder back onto the motor shaft. Be careful not to touch the video heads with your fingers. Make sure the head is correctly aligned, refasten the screws, and resolder the wires to their proper terminals. After the motor and head cylinder have been installed, the video drum should be cleaned. Next, use a factory alignment tape to check the proper tape height. If tape height adjustments are necessary, you should follow the recommended manufacturer's procedure outlined in the service manual. You have seen that VCR magnetically places the audio and video information onto the half-inch VHS tape. The video information is placed on the tape using the helical scan method to increase the writing speed necessary for the higher frequencies used in the video signal. The video signal is placed on the tape using azimuth recording. The azimuth recording is used to reduce the crosstalk between the two heads during playback. At a speed of 29.97 revolutions per second. Since the VCR uses two heads for record and playback, it will record or playback at 59.94 fields per second. This is the vertical field rate of a color TV. Each time a video head makes one track across the tape, it produces one field of information on the TV screen. The video drum is controlled by a servo system. The servo system must have a reference signal and a feedback signal. The vertical sync pulse is used as the reference signal during the record mode, and the divided down 3.58 MHz signal is used as the reference signal during playback. The speed of the servo system is adjusted by an electrical brake that is used to increase or decrease the magnetic field produced by the brake coil. This in turn will allow the speed of the video drum motor to increase or decrease. The video drum servo has two feedback signals, the FG pulse, which is the feedback signal for the speed loop, and the PG signal, which is the feedback signal for the phase loop. The FG pulse is created by a frequency generator, and the PG pulse is created by a pulse generator. The phase of the video drum is controlled to ensure that head A reads the track recorded by head A, and head B reads the track recorded by head B. You have seen that for VCRs to be compatible, they must have certain components that are identical in function and in the same approximate location. All VHS VCRs will have an erase head which has an AC signal applied to it in the record mode, usually around 65 kHz. They will have a video drum with 2, 3, 4, 5, or even 6 heads mounted on it. They will have a capstan motor which is used to control the speed of the tape through the VCR. They will have a pressure pinch roller which is used in conjunction with the capstan motor. They will have an audio control head stack that is used to place the audio information across the top of the tape and control pulses across the bottom of the tape. They will have loading posts and roller posts, and a tension arm, a supply roller. These are used to wrap the tape around the video drum in the play and record mode. They will have a sensor lamp that is used in conjunction with 2 phototransistors to let the VCR know when the tape has reached its end in either the forward or reverse direction. They will have a supply roller that is used to remove tape fluctuations before the tape wraps around the video drum. They will have a supply reel and a take-up reel, which the cassette sits on so the tape can be fed out and then back into itself. You have seen that the capstan motor is controlled by a servo system that is similar to, but not identical to, the video drum servo. The reference signal for the phase loop on the capstan servo is a 3.58 MHz signal. During playback, the feedback signal is taken from the pulses recorded at the bottom of the VHS tape. During record, the feedback signal is taken from the capstan FG signal. The capstan FG signal has 3 different frequencies, depending on the tape speed. 2,160 Hz for standard play, 1,080 Hz for long play, and 720 Hz for super long play. The capstan servo controls both the speed and phase of the capstan servo motor. You have seen that the method that the videocassette recorder uses to record the chroma information is quite complex. First, the color signal is removed from the composite video signal. Then it is down converted to 629 kHz, achieved by mixing the 3.58 MHz color burst with a phase-shifted 4.208 MHz signal. The difference between these two signals is then recorded onto the VHS tape. The color signal was limited to a 1 MHz band width. In the playback mode, the color signal was removed from the luminance signal by means of a comb filter and low-pass filter. The 629 kHz phase-shifted color signal was then processed through another converter circuit, which mixed the color signal with a phase-shifted 4.208 MHz signal to raise the color signal back to a replica of the original 3.58 MHz color burst. How the luminance signal was converted to an FM signal, which deviated from 3.4 to 4.4 MHz. The lower sideband of the luminance signal below 1 MHz was attenuated to allow room for the lower frequency chroma signal. In the playback mode, we saw how the luminance signal was demodulated back to a duplicate of the original signal. You saw that the audio circuits were much like the audio circuits found in any cassette recorder. They were simple, straightforward circuits that only required single injection and scope readings for troubleshooting most problems found in these circuits. In this tape, you learned a 9-step troubleshooting procedure which could be used for any of your repair jobs. By simply asking the right questions and checking the performance of the VCR, and by understanding how the VCR circuits work together, you can determine in what section of the machine the problem is most likely to be contained. Making voltage checks and scope readings, you can quickly narrow the trouble down to one circuit. Once you have the problem narrowed down to one circuit, you can use voltage and resistance readings to locate the defective component. You saw the procedures for replacing the video drum cylinder, the idler roller, and the video drum motor. You now have knowledge of how to professionally clean the entire tape path in the VCR. We hope this tape has helped you in your understanding of the VCR and how it functions. If you do not understand how a part of the VCR works, then rewind the tape and view it as many times as necessary so your jobs will become quicker and more profitable. Thank you for being one of our valued customers at Ucando Educational VCR Products Company.